We can now begin to talk about stage 2 of the implementation sequence. In this stage, we are attempting to reduce the coupling of the circuit diagram to make it fit more into the form of the mechanical system that we are modeling, which has no coupling or limited coupling, in particular no coupling at the ground. We have introduced the component, the neutral ground circuit, and so we have it here, and we will use it to reduce the coupling. And this is what we do. Where we had the circuit connected to a single ground, we now give each block its own independent neutral ground. So we have G1 being the neutral ground for the first mass, and G2 being the neutral ground for the second mass analog. And now, after we've done that, the next thing we do is to add voltmeters to measure the outputs. There's a voltmeter here and a voltmeter there on each block. And we also now identify the ammeter as measuring current that's going into and out of each block. The current will always be equal and opposite, just as our force is in the mechanical system, and the ammeter measures that current. So to implement this part of the circuit, we require something like a 4-channel oscilloscope. That would be the perfect instrument. Of course, if you have several ammeters and voltmeters lying around, which I know most people have more than one of those, then you can use those as well. So we connect the voltmeter across C1, representing M1, and C3, which is part of the variable mass when it is on this circuit. And this voltmeter will give us the output. If you have one that can differentiate the capture signal, then you will get the voltage per second, which represents the acceleration. But the instantaneous voltage that you measure, each independent voltage point that you measure in time, represents the velocity, which is the flow variable. Similarly, the ammeter measures the current going into this block or out of this block, into this block or out of this block. So it depends upon the direction of the current as to whether this block is experiencing a force that is positive or negative. This block has its own voltmeter as well. It measures the same type of parameter, however, it is coupled in parallel to C4. So remember how the differential variable capacitor works. When you rotate the shaft, this capacitance will go from perhaps 0 to its maximum value, and in parallel to this capacitance, they add to a single capacitance. And when you rotate the shaft in the opposite direction, this now goes down to 0 at the same rate that this capacitance C4 goes up to its maximum value. And it is in parallel with capacitance C2, so we have a capacitance adding again. This is the equivalent action to a mass flow from mass 1 to mass 2 in the mechanical system. And these voltmeters and this ammeter captures the changes as they go along. And if you're using an oscilloscope, it will record this in the time domain, and you'll give waveforms that you can analyze. So a 4-channel oscilloscope would be the perfect device, or if you have a 2-channel oscilloscope, you can use it to measure one voltage in the current, or both voltages, and using another ammeter to measure the current. But the important thing we have done here is decouple these blocks by giving them each their own neutral ground connection. This model is good for evaluating the system response to mass flows. So you may not even want to include the force in all of these experiments. You may want to find out what happens when you just rotate the knob on the differential variable capacitor to move the equivalent mass from here to there, and from there to there, back and forth. The ammeter will show if any voltages or currents should just show up without there being an input current. If currents show up from the rotation of the variable capacitor knob, and that means that the mass flow will be generating forces in the system. Here we are at the final stage of developing our mechanical analog in electrical form. Notice now that we have added some components to the system, one being the motor. This motor is connected to the shaft of the differential variable capacitor, and its purpose is to rotate that shaft for us left and right. And this motor is connected to a motor speed control circuit, and the purpose of the motor speed control circuit is to control the rate at which the differential variable capacitor shaft is rotated. So if the motor is attached to the differential variable capacitor, we call it DVC, that turns at the same rate in both directions, then we can calculate the mass flow rate that we were simulating as the capacitance range of the differential variable capacitor divided by its full rotation time. This rotation time can be seen in the waveform as the area between the dotted line. This is the time where the capacitance is sloping up or down. That is the full rotation time. And we can use this motor speed control to set this rate at a desired value. So the complete circuit is shown here with an ammeter and current source combination represented by the symbol between the M1 and M2 capacitor blocks. Each block has its own independent voltmeter to measure the analog of velocity. Going through the waveforms, we can see how the simulation should proceed. We'll start, say, with the capacitor C4 at its maximum value. And while that state exists, we turn on the current source with a positive current, and that simulates a force pushing these two masses apart. That current stays on for its desired time, and at the end of that time, the motor rotates the shaft of the differential variable capacitor, so that now, as the capacitance C4 goes to 0, the capacitance C3 goes to the maximum capacitance value at the same rate. After this motor speed control rotation of the motor is complete, we now reverse the polarity of the current source, and this is equivalent to a force trying to pull the two masses together. We let that go on for our desired amount of time, and the voltmeter measures the voltage waveforms that result. The ammeter measures the current waveforms, and from these waveforms we equivalently divine our voltage and velocity events in the mechanical circuit. Then we repeat that sequence, going back by rotating the shaft in the opposite direction so that C3 goes to 0 at the same rate that C4 goes to the maximum capacitance again. And once that rotation is complete, we turn on the current, this time in the positive direction, again simulating pushing the masses apart, and the ammeter and voltmeter captures those waveforms. Rotating the shaft now to reverse the mass flow back to C3 and off of C4. Current turns on in the opposite polarity, simulating pulling the masses apart, and so on. We continue this sequence until we have a certain amount of waveforms, maybe 4 or 5, from which we can find out the behavior of the mechanical system through the behavior of the electrical system. Notice that the waveform shows that we have a 120-degree difference between when the capacitance starts to rotate the shaft so every 120 degrees we get a rotation of the motor speed control. That is the phasing of this simulation sequence. So now looking at this, you have the basic information that you need to build an analog computer to simulate the mechanical system. In the actual implementation, you may discover that you may have to put in some resistances and other components for safety's sake to protect your ammeter, voltmeter, and circuit components. As long as you do the same thing to both blocks of the circuit and mathematically take into account what the effects of these additional elements that you might add may be, then you will be okay with this. Good luck, and thank you for attending this lesson.